Today, let's have a look at this limit problem. It says given alpha greater than 0, what's the limit of 1 to the power of alpha minus 1 plus 2 to the power of alpha minus 1 all the way up to n to the power of alpha minus 1 over n to the power of alpha. So in this case, we'll just divide both the top and bottom by n to the alpha of n to the power of alpha minus 1. Then we can have n at the bottom. Then we can have, because like I said, divide by n to the power of alpha minus 1. So here we have exactly the same power, except we just have 1 over n to the power of alpha minus 1 plus 2 over n to the power of alpha minus 1 all the way n over n to the power of alpha minus 1. Right? So it is 1 over n sigma sum k from 1 all the way up to n k over n to the power of alpha minus 1. Now if we let fx equal to x to the power of alpha minus 1, of course, this 1 over n times sum k from 1 to n. So k over n, right? K over, right? That is f of k over n. Right? That's exactly that. Right? So here we just look at the definition of Riemann sum. 0 to 1. If I partition this closed interval into n even parts, right, each interval, its width is 1 over n, right, this 1 over n, 2 over n, all the way, n over n, that is n minus over n. So it's like you take the width of each small interval and you multiply by the value f of x is taken at the right edge of each small interval, that is f of k over n, k equal to 1, 2, 3, all the way. Right, that is exactly the definition of Riemann sum. And if you let n approach infinity, you immediately get, this will approach 0 to 1 integral f of x dx. Right, 0 to 1. X to alpha minus 1 dx. Antiderivative is just x to the power of alpha over alpha. Because when you differentiate this, right, you get alpha times, right, alpha times 1 over cancel, alpha minus 1 becomes power. And take the value 0 and 1, you get 1 over alpha. Right? So this is only worth half the points if it was an exam, because in order for us to apply the definition of Riemann integral, first of all, it has to be a standard Riemann integral, meaning it has to be bounded. The function has to be bounded over 0 to 1. Right? You cannot have a function that's unbounded nearby 0 or 1. For example, if alpha is greater than 0, if alpha is greater than 1, we're safe, right? X to the power of positive power, right? You have the function bounded everywhere from 0 to 1, closed interval. But if alpha is smaller than 1, greater than 0, then all of a sudden we have a negative power. Right, then that function will look like a decreasing function, which is also unbounded at the neighborhood of 0. Right, in that case, we may not be able to apply the definition of Riemann sum and work out the limit. So we need a further lemma that says if, let's say, f of x is monotone over 0 to 1, open interval. In other words, the function doesn't even have to have definition at 0 or 1. And also if the right, let's say f of x is unbounded 0 and 1. And if the improper integral 0 to 1 f of x dx converges or exists, then we have the limit 1 over n sigma sum k from 1 to n minus 1 f of k over n must equal to the improper integral. Right? So if this condition is satisfied, then we can apply this definition of Riemann sum, right? Riemann integral as standard one, as usual, even though it is unbounded at these 2 points. Now let's prove this theorem so that we can apply the Riemann sum to this limit just like usual. So first of all, why is it the case that if f is monotone and satisfy these conditions, we can apply? So without loss of generality, we can assume that f of x is monotonously decreasing over 0 to 1. Like I said, f of x doesn't even have to have meaning definition at 0 and 1. Right? It's also unbounded. So if I can draw the graph, just sketch it roughly, I can say that, okay, let's do this. 0, x, y. Right? Imagine I'm partitioning 0 to 1 interval very, very densely. Even though I draw it big, but just so you know that it's very dense. Right? So in this case, so this, for example, 1 over n, that is 2 over n all the way. This 1, so 1, that's n over n, and that is n minus 1 over n. Right? We have n small intervals. Now, imagine if I choose n to be big enough. Right? It says 0 to 1 improper integral exists. Right? What does that mean? Right? That means if I choose n to be big enough, then I have 1 over n will be small enough. In that case, like I said, imagine if it's decreasing, right? So let's maybe draw it like this. Right, here it'll go up to positive infinity, and down there, right? Decreasing, and maybe I'll draw it like this. Down here it'll go to negative infinity. Right? Negative infinity. So, like I said, if I look at this area, from 0 to 1 over n, this curved area stands for 0 to 1 over n f of x dx, right? Which absolute value, maybe not, right? Or maybe at absolute value, whatever. So this can be small enough. Can be small enough. In fact, I don't even need absolute because it's approaching positive infinity, nearby 0. So when 1 over n is small enough, I can make sure that this curve is above x-axis. I can definitely do that. That is definitely achievable. Right? It's smaller than epsilon. Same thing, right? If I choose n to be big enough, means, remember, f of x is approaching negative infinity. So if I choose this interval to be small enough, I can make sure that this point, right, this point is below x-axis. Right? So in other words, the area is curved shape area from this to this, right? Its absolute value, like I said, from this point, that is n minus 1 over n all the way up to n over n, f of x dx can be small enough. Right? So, okay, given any epsilon greater than 0, I can really find a n naught when n is bigger than n naught. Right, this is achieved. And also at the same time, if I look at, because I want to show that this is true given these conditions, right? So let me just look at the absolute value of 1 over n k from 1 to n minus 1. We don't start from 0. We don't end at n, is because, like I said, f of x doesn't even necessarily have to have definition at 0 and 1. So f of k over n, I want to minus improper integral from 0 to 1 f of x dx. I want to show this can be small enough. Before that, I can just rewrite this, right? So first of all, copy this. Then this can be rewritten into 3 parts. First, I'll start from 0. Then I'll end at 1 over n f of x dx. Second part is that I start from 1 over n up to n minus 1 over n. Right. So third part, I'll start from n minus 1 over n up to n over n. Right, 3 parts. So first part, second part, third part. Right, so again, motivation is simple. I just, first I have this, then I want to look at the difference of these. Okay, so once I have this, I can just simply less than or equal to, I'll combine this and this. Right? This part means this part integral. Right? And we can integrate this is because like f is monotone. Right? It's only unbounded nearby at the neighborhood of 0 and 1. So which means we definitely, over this closed interval, we definitely have f of x is Riemann integrable. And also bounded. Right, so the Riemann integral, right, we can do. So once I put these together, I can say less than or equal to 1 over n k from 1 to n minus 1 f of k over n minus 1 over n f of x dx. Right? And then I can just put this absolute value, right? 0 to 1 over n, right, plus absolute value n minus 1 over n, n minus 1 over n up to n over n, right? Another integral. So these two integrals, like I said, I've already shown that they're small enough. Right? Can be less than or equal to, for example, epsilon plus epsilon, 2 epsilon. Right? As for this absolute value, like I said, I can, first of all, this is a standard Riemann integral from this point to this point. And this is the Riemann sum, right? This is sigma sum, Riemann sum, from exactly from 1 to 1n minus 1, instead of 0 up to n, right? So that 1, this matches with this one, n minus 1, n minus 1. Exactly the same starting point and ending point. Right, since it's a standard Riemann integral, right? So which means Riemann sum, when n gets big enough, their difference can be small enough. And you have this, 3 epsilon, right? When n is big enough. For any epsilon greater than 0, this is achieved, right? But it's okay if it's not epsilon, right? 3 epsilon is okay, right? It's like arbitrarily small, right? Doesn't matter. If you just use epsilon over 3, then eventually you get epsilon. So that doesn't matter. Right? So then we can safely say that, right? You can apply the Riemann sum as standard one to this one.